Hello again, welcome to the second week of this course on teaching mathematics in the junior secondary school. One of the things we talked about last week is this is only a relatively short course and we've got to cover up to 4 years of the school curriculum. So we're not going to try and cover everything, we're just going to try and cover some of the key ideas and some of the things that may seem difficult or uncertain about how to teach them. But whatever you try out and learn in your tutes and through these lectures, you then got to see if you can apply it to different curriculum areas and topics that you cover in the junior secondary school curriculum. Because the junior secondary includes everything from grade 7, 8, 9 and even possibly 10. So it's a big area to cover. Nevertheless, as long as you have a go and try things, the main thing is to try and rethink how you experience mathematics teaching at school. Now I'm sure some of you had some very good mathematics teachers, but it's not the only way it has to be. There's lots of different ways you can do it. You have to find ways that work for you. The other thing we think is important is whatever you think your style or approach is, you've got to have some variety. You can't just do it the same way all the time. So this week we're looking at number and numeracy. There'll be 2 videos this week. And this is the first one where it's more of a general overview. Yeah, it seemed funny at the time when I saw it. Maybe you don't think it's so funny. And given current prices, probably cost a fortune anyway. All right, so my first question to you is, what are numbers? You've deal with numbers all the time. Everyday part of your life. Now, you don't need to come to school to learn most of your things you've learned about numbers. You've learned them at home or doing various things, and sometimes, remember though, the numbers are used in different ways in different contexts. So for example, if you are watching the cricket and someone's bowling, let's say they're bowling their 7th over, then if you look at the under the over number, it'll say 6.1, 6.2, 6.3, 6.4, 6.5, 7. Now you can see their numbers are used differently than how they might normally be used, at least in a mathematics class. You can see the context there makes them mean something different other than what we normally think when we consider them in base 10 place value. Also, if you think of little kids, you ask them about numbers. Well, numbers, of course, are the things we understand about quantities of things, but also often their class has a number. So if you say, what's 7? And they might say, well, it's the room down the other end of the corridor or something like that. So sometimes numbers are used to name things or all sorts of other things. So just remember, in the context of real life, we use numbers in a range of ways which we cope with fairly well. Anyway, let's have a little think about some of these numbers. Do you think these are numbers? 1, 2, 3, 4, etc., etc. Almost everyone I've asked would say yes, they're numbers. Why are they numbers? Well, because they represent the quantity of something is usually what people will say. Okay, so if we're happy that they're numbers, and if you're interested in knowing, they're called the natural numbers. Actually, they're called the whole numbers. Sorry. What about 0? Is 0 a number? It doesn't represent the quantity of anything. In fact, it represents a quantity of nothing. It means there's nothing there. Now, you've got to remember, in some cultures, they don't have the number 0 because you don't need it. Why do you need a number for 0 if there's nothing there? You wouldn't say, I've got 0 pigs, or I've got 0 Ferraris. It's obsolete, it's unnecessary. Yet we seem happy enough to accept it as a number. Now 0 with 1, 2 and 3 are called the natural numbers. Sorry, the whole numbers, natural numbers. All right, what do you think about these? Are these numbers? -3, -2, -1, etc. Now certainly these things, you can't show these as a quantity, as in something physical you can hold. They don't represent a physical thing, but they do conceptually represent something. And it's at this point some people start to get a bit iffy about whether they're numbers or not. In fact, they are numbers, but they're not in the sense that they represent a quantity of physical things, a cardinal type number, I suppose you might say. All right, if you're happy to accept those, would you accept these as numbers? 1/2, 3/8, 1 1/3. Okay, obviously fractional numbers, particular sorts of fractional numbers, ones that we can write down as an exact decimal. We can give them a precise definition. Now, some people are quite happy with these as numbers. In fact, most people are happy with these as numbers. All right, what about these numbers then? 0.5, 2.23. And in fact, with the last dot point, these would be all considered fractional numbers. And again, most people are happy with these being seen as numbers. All right, what about these two numbers? Pi, e. These are called irrational numbers. The ones above are all called rational numbers. They're called rational because you can write them down exactly. These two numbers you can't actually write down exactly. So probably the one you're most familiar with is pi. Pi being the ratio between the circumference and the diameter of a circle. And most of us would say it's 3.14 or 22/7 or something like that, but it's only an approximation. And in fact, pi you can write down to as many decimal places as you like, and there'll be no repeating pattern to the digits. It's a number you cannot write down exactly. So are you happy that these are numbers? And if you're happy with those, e being the natural number, what about this one, I? Now at this point, a lot of people are saying to me, nah, that's not a number. All right, I was originally called I because it was the imaginary number, which again is a funny term because it sounds like you close your eyes and think of a number, but I is defined as the square root of -1. Why did we make this a number equal to the square root of -1? Because we had a problem which had the square root of -1 as an answer. We couldn't find an answer, so we made one up and we called it I. It's not really an imaginary number, it's called a complex number, and we'll go into that in more detail if you're doing secondary maths. Now the point is here, some people will get really upset or won't accept that I and E and pi are not real numbers. They're not numbers, they're just ideas. But in fact, all numbers are just ideas or concepts. It's a way of representing something. If you're happy with 1/2 as a number, you can't actually show me 1/2. If you had an orange or something and you cut it into two pieces, you haven't got 1/2, you've got 2. There's 2 pieces there. And even if you could do it, it still wouldn't be 1/2 because there's no way you could get it exactly into 2 pieces. So numbers are concepts or ideas. And all of these are numbers, and they're just concepts that represent different things. We've come up with something and we've given it a name, and then it's proved to be useful. Okay. What about these numbers? Now, I'm trying to show you this way. Sometimes you see, particularly younger students and in your classes, even if you're secondary, you're going to get kids coming through who are pretty limited in their mathematical background. But which of these are numbers, or where did they come from? Where did 11 and 12 come from? Why have we got this special word 11, which doesn't seem to mean anything other than the quantity that just one more than 10? And 12, where did 12 come from? Why do we have to have this special word 12? Why isn't it called 2-teen or something like that? And then you get to the next ones. You see the next one there, and here particularly look at the language. The next number is 13. As in ordinal number, third teen. So if you follow that pattern, what would the next number be? 4th teen. But no, we've gone back to cardinal numbers. We say 14. All right, so the next one must be 15. Oh, hang on, we've gone back to ordinal numbers again. It's 15, 15. And then the next one, not 16, but 16. So again, we've gone back to cardinal numbers. And then 17, 18, 19 are all using cardinal numbers, not ordinal numbers. But just the language makes it difficult because we keep switching it around. All right, and we do the same with our teens. 20. Why don't we call it 2T or even 2nd-T? But we call it 20. Third, and then we go 3rd-T, which is ordinal again. 4th-T, 4T as in ordinal numbers, 50, 60, etc. All I'm trying to show you is the language around how we say and record numbers in English is a bit confusing. Can you read this number? 716. So what I want you to think there is, which digits did you read? 7. Okay, so we read the first digit. 716. Okay, so we read the 7 first, then we read the last digit, the 6, and then we read the 1. 716. Why didn't we say 716? So you can see reading numbers can be difficult, and if you get kids, particularly who struggle a little bit, who get them around the wrong way, it could be a language thing that makes it difficult for them. All right, this is a bit on the side, but what's with these names? How many, what month in the year is October? It's the 10th month, 10th. But what does oct mean? 8. So why is the 10th month called October? Why is the 11th month called November, which means 9? And why is the 12th month called Dec, which means 10? Well, interestingly enough, the calendars used to have 10 months in it, and you'll notice in the middle now we have August and July, which happen to correspond to the names of Julius Caesar and Augustus Caesar, which then explains, if you're really interested, September also means 7, and it's the 9th month. So you can see there's some little weird things about numbers which we just take for granted, which might cause kids to slip up. Right, so we've talked about numbers, but the other thing we often talk about in mathematics is numeracy. Now, in fact, numeracy is supposed to be taught right across the whole curriculum, not just in maths. Because numeracy has been defined in different ways, and often it's sort of meant numeration, you know, addition and subtraction and things like that. But in fact, numeracy is the ability to use maths in everyday life, in other subjects, in community life, in things you do just around the house, etc. That's called numeracy, or applied mathematics, using mathematics effectively. So numeracy is definitely part of mathematics, but it should be part of your other subjects as well if you teach any other subject really. And the question is maths different from numeracy? Well, it is. In mathematics, and the curriculum says the emphasis is usually on understanding the concepts. Now, we can debate whether it's useful to talk about the concepts outside their use in a numeracy sense, but technically the mathematics is not necessarily about the use of mathematics. Although at school I would suggest it's really useful to put the two together. In numeracy, the emphasis on the use of quantitative, spatial reasoning, measurement skills, ideas from chance and data, and applying to everyday things like shopping, reading the newspaper, looking at a report, all those sorts of things, building something, playing sport. So you can see the difference there. Now, it's a little bit semantical sometimes to talk about the difference, because you should be doing numeracy in mathematics and often together. But if you're in another class, another subject area, you won't probably do mathematics, but you should be doing numeracy. Now the question is, can someone be numerate without being mathematical? Well, obviously they can. One time I met a plumber. He was an outstanding plumber. He could do all sorts of things in terms of the fall of the drainage pipes and all those sorts of things. But he didn't know any school mathematics to save his life. So he was very numerate, but he wasn't very strong in mathematics at all. The question is, does learning mathematics help you be more numerate? Now it should, but I think often we need to do more to help students see the mathematics and its relevance to practical contexts. Otherwise they don't see the relationship. So I want you to think a little bit about numeracy. Now often in numeracy we'll start with some sort of real problem. Real as in, I'm not sure what a pretend problem is, but some sort of real problem, something that might be relevant to the students. And then you'll do some sort of modelling to build a mathematical problem. So for example, you might want to know how much fertiliser you need to put on your front lawn. That's supposedly a real problem. And then what you might do is draw a diagram of your front lawn, which is a rectangle. So that's therefore modelling your front lawn with a diagram, and therefore it becomes a mathematical problem to try and find the area. You'll then find a mathematical solution using mathematical procedures, and you'll find the area of the front lawn, and then you'll work out how much fertiliser you need based on how much fertiliser you need per square metre. And then you'll translate back to the real solution where you'll go and measure out the fertiliser, you'll put it in your little spreader thing, and you'll spread it around the lawn. And then what you'll do after that is you'll probably just check to see if it's okay. So that's one way of looking at numeracy. Very simplistic, but often that's what it might look like. You can talk about this more in your tutes if you like. But the question I have is, in mathematics classes, this is all we seem to do. And the assumption is if we do this part with the students, then they'll be able to do the rest of it themselves. And the evidence is pretty strong that they can't. So while it's not unimportant to do the part in the circle there, the ellipse, it's really important that you build it in as part of the broader numeracy cycle of learning. And in fact, these days the part in the ellipse shape there is probably the easiest part. In many respects a machine can do it, but a machine can't do the other parts often. So helping kids to be numerate is really important, and knowing mathematics and being able to do mathematics is a small part of that. So here's an example you could do with your kids. And I used to do this one quite often. My students would come in at the start of the year and I'd want to get to know them. I didn't know them, so I'd say, okay, here's a big piece of paper, or you could do it on a Padlet or something if you wanted to. Draw your hobby in the middle, whatever your hobby might be. Something you're willing to share with everyone in the class, or something you're interested in. Okay, now your job is to go away and brainstorm all the mathematics involved with that hobby. So the students would go away, and if they were interested in surfing, they might talk about the shape of the board, the height of the waves, the frequency of the waves, blah, 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 blah. And you could try this with whatever your hobby is, but almost always there's a whole pile of mathematics involved. Whether it's a sport or a craft or something, there's always some mathematics involved. And then the students had to come back and present what they found out. So the interesting thing was, a lot of the students found there was a lot of maths involved in the things they were doing every day. And that was quite a revelation to them. And it sort of helped them to try and see maths as more relevant. It also gave me some ideas as a teacher of some things I could include over the year to help connect them in. The other thing is, if a student said to me, look, this activity is really boring, and I'd say, well, don't blame me, it's your hobby. If your hobby's boring, it's not my fault. So it was a chance to get them to be interested by starting with what they were interested in and drawing the maths out, rather than starting with maths and trying to put it on top of what they might be interested in. It worked pretty well, and it's a pretty easy thing to do. So some final points. You can't develop numerate adults at school. So if your goal shouldn't be to try and help them become numerate adults, you can only develop numerate kids. And what that means is you need to use context and ideas and things that are of interest to the students. So numeracy is when you use mathematics in something that's useful and meaningful and relevant to you. So again, I can give you a wonderful example. When I was teaching, I did percentages, and I had this whole fantastic unit on mortgages. And I did it with the kids and they just weren't interested at all. Because it was numeracy for me, as someone who was getting a mortgage or had a mortgage at the time. It might have been interesting to their parents, but most of them were renting, to be honest, at that time. But it wasn't relevant or interesting to them. It wasn't numeracy for them. And it's no point saying, oh, but you will get a mortgage one day. It doesn't enter their realm of interest or capacity to be meaningful at all. So try and choose things that are of interest and relevant to the kids. And if you do that, you can often be halfway to getting them to be engaged in their mathematics. Anyway, that's just an introduction to numeracy and number. Hope there's some things that made you think a little bit there. And again, you can pick up some of those with your tutors if you wish. All right, thanks for listening, and I'll see you in the next video.